Test. So, good afternoon, ladies and gentlemen. So, sorry that we have to start a little bit later. So, we try to speed up so that we be ready in time, so you can enjoy the rest of the Green Tech Fair. So, you're very welcome at this session. It's about LED lighting in vegetables, greenhouse vegetables, especially tomatoes and cucumbers. And we will do this, the three of us. Caterina, she's from Wageningen University Research. Silvester is also from Delphy, and my name is Eric Poot. I'm also from Delphy. See if this works. Yeah, so maybe, I don't know if you all know Delphy, so I take the opportunity to introduce our company a bit. We are a knowledge company. We help growers to improve their cultivation. That's mainly the core of what we do. And we have a few different business units where we work in. So most of my colleagues work in consultancy. So they give consultancy to growers, they give advice to growers how they can improve their cultivation. They are not only active in the Netherlands, most of them are, but we work all over the globe. Some colleagues of mine from the Netherlands, so they fly all over the world and they use digital tools more and more. But of course, a lot of them also work from home and travel around and visit the growers at their greenhouses. So Silvester and I were both from the research part of Delphi, the improvement center. It's applied research what we do. We try to develop knowledge that also our consultants can use to help growers also again to improve their cultivation. Then we have Delphy International. They do a lot of projects all around the world. This is a picture from Sub-Sahara, but I saw in the booth that we have also a lot of visitors from our Delphy International colleagues from the Middle East, for instance. We have a Delphy Academy, and this Delphy Academy trains professionals to get a higher level of growth knowledge. And then we also have Delphy Digital, and Delphy Digital, they develop tools, digital tools, which also help growers to improve their cultivation, to have a better prognosis of their harvest and these type of things. If you want to know more about these activities, you are more than welcome in our booth and we can explain more what we are doing. This is about LED, and a colleague of us, Anja Dieleman from Wageningen University, she described earlier this year 5 different trends in LED lighting, and I'd like to start with that. The first one is the shift from high pressure sodium lights to LED light. I think that you're all familiar with that. In the Netherlands we saw the last 2 winters, I think, that a lot of growers shifted from HPS or hybrid lighting systems, so the combination of LED and HPS, to full LED. And for instance, in tomato, but also other crops, full LED lighting is now the standard. A lot of work has been done by research stations like Delphi and Wageningen was on to optimize the light spectrum. That's one of the big advantages of LED lighting. You can give quite precise the light that the plant needed. And we think that we now, for most crops, the most important crops at least, we know what the optimal combination is for tomato, cucumber. It's about 90% red, 5% blue and 5% white. For cucumber you definitely need far red. For tomato it is not necessarily. And for other crops we're still making slight progresses in optimizing the LED spectrum, and it's also done at the companies itself. The third trend in LED lighting that Anja Dieleman found is the trend to dynamic lighting. So HPS was on and off. With LED lighting, and then when you turned it off, you have to wait a while before you could turn it on again. With LED lighting, it's much easier to put it on and off. And especially with the prices of electricity, and you can see the graph over there. There are times at the day that the electricity price is very low, so that can be very interesting to put on the lights when the electricity price is low. So a number of projects we are conducting now, both in at Wageningen as at Delphy. The fourth one is that, well, okay, we have more options with LED lighting. Also this dynamic lighting gives a lot of extra options, but you need to incorporate it in a cultivation strategy, an integrated strategy. And for an integrated strategy, you need to know when you want to sell the ripe tomatoes or cucumbers to your clients. And then with all the knowledge also in growth models, you can calculate, okay, what is the cultivation strategy that I need to follow to get these results. And within this cultivation strategy, you have to think about, okay, what is the light strategy that I can follow. Still, in this fourth stage, what's necessary is that you have a plan, but you also need a lot of measurements, and not only on climate and on light output and these type of things, but also on the reaction of the plants. So what we do now still a lot is doing measurements by hand. For instance, the thickness of the head of the plant, or calculate the leaf area index, and these are all data that needs to be put in the growth models which we use to predict the harvest. So the fifth one is that also these type of measurements, plant measurements, are removed by sensors, and all these sensor data are incorporated in new models and new algorithms, and then also the artificial intelligence come in. And that is where we are, I think, now doing the first experiments also on the talking plant. So the plant is telling to the model how they react on what's given to them, and in combination with the growth strategy that you have, yeah, this is a very smart combination. But all these options, one of the biggest things that's different with when you cultivate on LED light is that you have a much higher output of light and a much lower output of heat, and that influences the crop. So in a number of crops, we saw the last 2 winters, we saw some problems with quality, for instance, and talking with growers, okay, what is the reason that we have under LED lights these problems? And they all say it has to do with we have lower heat emission from the lamps, so it must be the evaporation. So we started, I think 2 years ago, the first experiments on to get a grip on this, on what's happening here with the evaporation of crops under LED lighting. And this project is called the Master Plan of Evaporation, and I think this is the bridge to give the floor to Silvester.
Yep, thank you. Deze knop. Okay, so my name is Silvester de Nooijer. I'm team leader for the research team at Delphy. I would like to show you something of the results that we have in our research on what happens if you reduce the amount of evaporation under tomato that is growing under LED lights. So we did now 2 years of trials in a greenhouse, large cluster tomato as pictured here under LED lighting. And the question that we're trying to solve is, I mean, if the problem with growing under LED is that the amount of evaporation drops, how much is really needed? So that means that we had to measure the evaporation, and we do that through a water balance. So that means that we have we weigh the plant, the mat. We weigh the amount of water that goes in. We weigh the amount of water that drains out of the mat. And then, of course, there will be a difference, and that's the amount that the plant evaporated. So we have in 2023-2024, so the previous growing season, we had 2 greenhouses, each of 150 square meters at the improvement center. And there we had one greenhouse where we put a very high humidity, and the other one we put a low humidity. So what's high? It meant that we put a humidity deficit at 2 grams, whereas in the other greenhouse with low humidity, we kept it above 3. In each greenhouse, we also did a different fertigation strategy. So in each greenhouse, we gave parts of the plant a high EC in the water and other part rather low EC. And then we checked how much evaporation does that give. Well, these are the results that we got. So you can see here on the graph on the right, see if the pointer works. No, I just have to point like here. Here in this graph, you can see the average humidity deficit that we realized. And you can see that indeed in the greenhouse with high humidity, in the night we were about at 2, and in the other one slightly over 3. Here's a graph with a relative humidity expressed in percentages for those who are more familiar with that. And here on the right, here on the left, you can see the effect that had on the evaporation. And that graph shows, well, basically the result that we expected. If you have a high moisture and a high EC, that's where the lowest amount of evaporation occurs. And then if you go to lower EC, it goes up. And it also goes up if you move to, if the air is less humid. Then of course the question was, what's the effect on the crop? Well, first effect that we saw that year was a severe attack of botrytis. Well, it's logical, you grow under high humidity, so that means that the plant can more easily get infected by the fungi. It entered through the edges of the leaf, so the edges of the leaf are also a bit sensitive under LED. That's where the attack happened, and then it just went into the plant. And it also entered through some leaves that were damaged by edema. We've also seen that despite the fact that we had very low evaporation, the fruit quality was not really affected. And that was expected because low evaporation tends to mean problems with the amount of calcium going to the fruits. And therefore fruit quality problems, but we didn't see that. And finally, we saw that the fruit weight was lower at the high EC and low relative humidity. And that resulted also in a lower yield in the end. So those were the effects on the crop. Then, because we couldn't really go lower in evaporation because of this botrytis problem, this year we tried to solve the botrytis problem in a different way. And we did that with an air circulation system, which is shown in this photo. So you can see under the gutter is a tube, and this tube is air is blowing out of that, and the air is coming from just above the crop. So we don't have any air treatment, we don't heat it up, we don't dehumidify it, we just recirculate through the greenhouse by sucking it up above the crop and blowing it out under the crop. Again, we had very high humidity, and we did this, we made a variation in the amount of air that we recirculated. So in part of the in one greenhouse we did 7 cubic meter per square meter per hour, and in the other 16. So we had a low and a high amount of air circulation. Well, what we saw was that the evaporation was even slightly lower than in 23-24, but we had botrytis very well under control. So we didn't have any significant problem with botrytis. And it seems that by recirculating the air, you put relatively warm, dry air in the bottom of the plant. It will go up through the plant, will keep all the air moving, and therefore the conditions don't get so humid in between the plants that the fungus can grow. Now, other things that we saw was that, again, we had leaf quality problems. So where in the first year the leaves got infected with botrytis, now they didn't get infected, but they were still damaged by just the lack of evaporation. So we saw like the leaf edges getting damaged, and we also saw the leaves, especially the oldest leaves, really turning yellow. And again, we also saw these small fruits with a lower yield. So looking at all these trials that we did, we can conclude that low evaporation is not in fact the cause of all the problems that occur under LED. So it does have the effects that are that can be attributed to low evaporation are the leaf edge wilting, the yellowing of older leaves, and the small fruit size. But again, this trial we saw that the fruits colored quite well. And the reason that that is that is working in our greenhouse is that near this, if I show you the photo again here, that in this photo, near the ripening fruits, we have these heating tubes. And by using these growing tubes in this photo, we can avoid that the fruits get too cold, and therefore, because the fruits are warm enough, they attract the nutrients and they grow out just fine. So they get and they have good coloring and good development. And yeah, we conclude that botrytis can really be controlled with the amount of air circulation. So, well, this puts us a step closer to understanding where the problems are under LED and what we can do about it. And our next step will be to try to grow and also solve these last problems. So the problem with the leaf and the problem with small fruits, because in the end we want to be able to grow under these conditions. So that brings me to the end of the part that I wanted to tell you, and now we will move to Caterina.
Yes. Thank you, Silvester. Hello, everyone. My name is Caterina Carpineti, and the small one? Nope. This big one? Yes. And I would like to tell you something about another part of the research that we are doing together within the master plan evaporation. In our case, it focuses on cucumbers. And I don't work on that alone, of course. I work also with other colleagues. You find the names there. Perhaps you recognize someone. We are all colleagues at the business unit, Greenhouse Horticulture and Flower Bulbs of Wageningen Research. Why cucumbers? Well, the general outline, it was already given by Eric. A number of issues that were noticed more and more in the previous years. And all these issues, for some reasons, they were attributed to evaporations, too little evaporations. What is that in the case of cucumber? You have flat heads, as you can see in the first picture, ball-shaped leaves. You get abortion, like you can see in the third picture, and misshaped fruits. Sometimes they are a bit like a bottle. Sometimes they have the exact opposite shape. And the point is that because the issue was always linked to transpiration, one of the action was trying to keep relative humidity low, like also Silvester was showing. But of course we know that exactly doing the opposite can save energy. So allowing a little bit more humidity and avoiding losing heat through, for example, opening the window together with your relative humidity can really save energy, as you can see in the statement here at the bottom. So what did we want to do? Well, we realized that there was some need to start to deepen the knowledge that we have about transpiration, understanding what is necessary, when is it necessary. In our cases, we started in these first 2 years with research in fully closed environment. We chose to go for in-depth research in which we would change one condition only and quantify what the effect and what the response would be of the crop. We did it as well with the water balance way. So in our case, we have a pro-drain system. And we did it also by looking more in depth at what happens at leaf level. So for example, with machines like the Lycor 6800. And the main point is really we want to know what the crop is experiencing, where the boundaries are of the crop, because once we know that, we can then also know how can we more easily or more safely steer the climate around it without having issues with yield in the end. As I said, we are now doing it in the vertical farm in Bleiswijk. We have the last trial running at the moment, and the plan for next year is get all the knowledge and apply it into real greenhouse trials. We did a lot of things, so I will try to squeeze as much as possible. One of the first things we focused on was indeed the humidity deficit. That's the most logical one because that's exactly what we want to be able to steer a bit more freely, perhaps. So what you can see here in the top left graph are all the different tests we did by varying humidity deficit, or VD, that's a Dutch abbreviation, during the day and during the night. And what you can see is how that connects to the final yield. And you can see that somewhere there between the orange and the yellow, let's say to make it simple, there is a cut. So something is happening that is causing basically all those issues that I showed you in the pictures before, which I think, as you can imagine, they came from my trials. They were pink pictures coming from the vertical farm. We try to look at what is then going on, of course, and we also try to come up with numbers where the growers can find themselves, and they can also test them in their own greenhouses. When we do this research, we have every 2 weeks a grower committee that comes and checks our cultivation and tries to learn, and we try to learn together. And one of their point was, for us, measuring transpiration is very difficult. Water uptake, it's a bit easier to measure. We can do at least irrigation minus drain, and you have your total water uptake in 24 hours. So that's the graph that you see here at the bottom. We basically translated the daily results into water uptake, and then dependent on the VD that we applied. And of course, as we could already expect, there is a clear linear relationship between water uptake, transpiration, and the humidity deficit that you apply. And to make it even a step closer to what the growers are now doing, we started expressing it in milliliter of water uptake per mole. In at least talking with our growers committee, that is what they were looking at, also in an attempt, in their opinion, to make it a bit more generalized, so a bit more independent to the light that you would use. And if you stay somewhere in our orange to red, you would find that for our cucumber, in our case is deflection, in our conditions, around 117 milliliter per mole par would be, let's say, the boundary. After all the research we have done on VD, those were all separate trials, so I think we've done quite 4 or 5 trials on that. We moved to a next environmental parameter that is interesting both from an energy perspective and from a transpiration perspective, and we moved towards light intensity and photoperiod. That's also because, as I just showed, what the growers use are the milliliter per mole. So there is already a component of light that they look at, and what we were actually curious is, can you always use it? So is it true that if you are using a different, for example, photoperiod, yet still the same DLI, that 117 milliliter per mole would still hold? So it is such an, applicable way of growing and of looking at your data. So what did we do? While our standard cultivation was 16 hours and a DLI of 16.5 mole per square meter per day, we deviated from that by increasing it to 20 hours. That is also quite common in winter production. Growers can also reach easily 20 hours of lighting. And we chose, of course, for another extreme, we were already at 16, which is not that long. So we went to 14 to still being in a long day and not going into a short day. And what we found was actually interesting. The old premises here is that transpiration is the issue, and all the issues we saw before, they are due to transpiration, and then you can use water uptake also as a way to monitor it in an easier way. In this case, what we actually found is that transpiration was not a problem. There was a very small difference between our 2 treatments, 5%, I would say not significant in this case. But if you look at the water uptake, then you do see that there was a difference. The long photoperiod had, on average, 15% less water uptake. And if you see it in yield, that was even more dramatic. The long photoperiod had almost 50% lower yield. Why was that? That was not what we expected necessarily. Why? We had the same DLI, 20 hours. As I said, it's quite common. It's not a weird way of growing cucumbers. But what we did since the beginning is we always kept the far red on only for a part of the photoperiod. It was a choice, so we didn't have it on continuously, but we always had it on for 8 hours. So we had it 8 hours out of the 14, or 8 hours out of the 20. And those were the results of yeah, just visually even what you could see on the crop. So the leaves start looking bleached. We measured the number of parameters. You can see there was 30% less chlorophyll content, as you can expect. The efficiency of the photosystem too, so part of the photosynthetic apparatus was quite less efficient, all compared to the 14 hours. And of course, the photosynthetic rate was quite low. And there you can see again the yield, but then per week, so they are exactly the same figures as the previous one. So arrived at this point, with the growers we discussed, okay, we need to understand what's going on, because apparently it's not transpiration, there must be something else. And we started wondering whether it was into these 8 hours of farad the issue, or whether perhaps the night was too short, because of course these were 6 weeks of continuously 20 hours a day, not only a couple of days per week with 20-hour photoperiod. So what did we do? We exchanged, or we lengthened slightly the project, and we moved this one with 20 hours farad. We just plug off a number of lamps, and we were able to keep always the same farad DLI, but then for 20 hours. And the 14 hours, that was already doing quite well, so we just wanted to try something in between. 16 hours was fine with 8 hours, so we moved it to 18 hours to see whether it would start appearing something like this. And what you can see from a production perspective, you can see that basically in both cases, they more or less recovered. That is to say, it's a crop with a history. Yeah? We didn't restart completely. It was the same crop that we extended. But you can see that the long photoperiod went back to almost the same pattern as the short photoperiod. And what is interesting is that actually moving from 14 to 18 also did something with production. It reduced it a little bit. And you can see it here as well. These are net CO2 uptake, so this is a photosynthesis measurement at leaf level. The 20 hours with 8 hours of farad, where we moved it to 20 hours of farad, it completely recovered and it became quite similar to the others at the same light intensity. While the 14 hours of par with 8 hours of farad, you could see it here as well, there was some slight reduction of photosynthetic activity. So what are the take-home messages here? First of all, we could show that indeed, if you have a low transpiration rate or a low water uptake, and those are the numbers for water uptake, you will see scrotched eggs, bowl-shaped leaves, abortion, so all those problems that were mentioned at the beginning. But the low water uptake can be there for different reasons. On one side, it is indeed to be due to transpiration. So in our case, we could see how the night humidity had or didn't have an effect, and how the 24-hour humidity can be limiting. For us, the night humidity was a really point of interest, and in the end, we could find that even by going as low as 0.8 gram per kilo humidity deficit, you do not see any issue on the crop, given that during the day you have enough transpiration going on. But it's also important to mention that sometimes issues with water uptake are not due to transpiration, but are due on something else that is happening on the crop. In our case, I have to be honest, involuntarily, we found it with the farad. And indeed, what you can see, and what is also known, is that if you have limited sugar, so you have little assimilates in the crop, that can also, of course, have a direct effect on your yield, and in that way also on the water that the crop needs to uptake to fill up. So with this, I will leave the word back to Eric, I think. Thank you for your attention.
Maybe an applause for Caterina and Silvester. Does it work? So this was a lot of information in a really short time. So I can imagine that maybe you have 1 or 2 questions for Caterina or Silvester. Is there Does anyone have a question for them? Yeah, okay, I'll come to you. First one is always the most important one.
Thank you for the presentation. I was wondering what you did about the height of the cucumber plant in your growth chambers. Were you able to use something representative of greenhouse production, or did you scale it back? And then follow-up is, what do you think about any option of sole source commercial production of cucumbers? I know a few maybe in Sweden are looking at it. Is it something you've considered?
So in this cell, we have a free height of approximately 3 meters. So I would say, let's say the space where the crop is hanging. So quite similar to practice. Of course, it's a fully closed system. So there is no sunlight effect in there. And you could say like, yeah, you are doing anyway winter type of research. You would have already quite little sunlight in there. But we are using them at the moment really as a research tool and to get basically high data amount and to focus really specifically on one component only, while in the greenhouse I will always have to come to terms with other effects. And that's also why in one of the first sheets I showed is we want to move later on to greenhouse to then also prove that what we are finding out here is applicable to a real greenhouse environment.
Any more questions? Yeah.
Thank you. Thanks for your talk. You saw that after changing the far red regime, the productivity was recovering, but still not to the level of the 14 hours trial. How do you interpret these results? Do you think the recovery, if you had extended the trial, the recovery would still increase? Or do you think this is related to the photo period difference? What is your opinion on that?
Yeah, what we cannot say for sure is whether it's only the far red or whether there is an interaction with the night length. So the fact that we have always this constant 4 hours long night, I do not know whether that is sufficient for a cucumber to completely repair and be able to start at its maximum efficiency the day later when we turn on light again. That's why I think it was even between brackets. Is it also the night playing a role? I cannot say it for sure.
Okay, thank you. Any more questions? So then it's in the front.
Thank you. One of my questions was, is there any photosynthetic activity that was used also during the experiment and measured, linked to the evaporation rate? Would you see any variation as well? Or
Your question is whether the evaporation is limiting photosynthetic activity.
yes.
What we can do with those cells, we can use them as a big chamber. They are airtight. So what I've been looking as well is at the whole crop CO2 uptake to see indeed whether there was a difference. And no, I could never really see that transpiration had an effect on photosynthesis, not a big one at least. I don't know if for you it was different.
Yeah, and in tomato we did some measurements with the porometer in this greenhouse and also did not see any significant difference between the treatments.
Any more questions? So then it's quite clear. So I think the message is quite clear. So I told you that a year, 2 years ago, we thought, okay, if you grow on the full LED light, then you have problems with transpiration. And these problems cause all kinds of problems in the crop and with the quality. But now it's more, as we say, it's more, how you call it, subtle. Some of the problems are related to evaporation, as what Silvester told us in tomato, but others not. If I ask you both, what is now the next thing that we need to find out to have really good recipes for growers that they can grow on the full LED without any problems? What should we find out?
Well, I think in tomato, what we want to know is, for a grower, The main issues that they are now encountering is this problem with the fruit color. We found a solution for that, which is basically bring back the old growth tubes that are heating the area with the fruits. With that, they can already take a big step. But this question is now how to get exactly the same amount of light use efficiency as as growers were used to under the high pressure sodium. There are some indications, we've been working on that recently, that it's still slightly, that the light use efficiency is slightly lower under LED as compared to high pressure sodium. We don't really know why, and so that's really, I think, the next thing that we need to work on. That's also the next thing that we're going to work on, we can now say. But
Caterina,
Yeah.
did you also saw the lower yield under LED, or did you not make the comparison?
I can speak in terms of light use efficiency at least, and I know that in terms of what we could achieve, we were always for cucumber around 24 grams per mole, which is a good one also compared to a greenhouse. So no, we could not really see a major difference, and of course it also has to do in the end with the plant density you use, so there are way more factors, and we were maybe a bit on the low side even for such a chamber. Well, the last conversations I had also with the growers and linked to the discussion on day length, far red, when and when not. One of the interest is in trying to understand, let's say, how efficient every hour or every couple of hours that you give to the cucumbers are. So try to understand when indeed during the winter as a grower I choose to extend my day because I have really little sunlight and I want to reach my DLI, those extra 2, 3, 4 hours that I add, how much are they really bringing me and how much are they asking me in terms of the energy input that I am using to give those extra hours. So that is something that we are going to continue on. For the far red, there is a lot going on. I have a lot of, not myself personally, but I have other colleagues working in understanding when to turn on far red, for example, for cucumber, when moving from summer to winter cultivation, and also there in a more, let's say, dynamic way of lighting to try to save some energy. And of course, what we are going to look at still, and also within this project, is I presented you the humidity deficit and light effect, but there are way more other things that you can play with and that you can use them to compensate if you want. So when you know that you're getting close to a boundary, for example, too close to limited water uptake, what if you could play with, for instance, lowering CO2 for a little bit to open more your stomata and help your crop transpiring? Or what if you could use other input, DC in the water, or other things like you also showed, to steer. So look at it more from an integrated perspective, so not just one effect at a time, but really try to make the most optimal scenario by integrating all the different aspects of cultivation.
Okay, thank you. So, any last questions from the audience? If not, then I like to thank, of course, Silvester and Caterina for their contribution. And I'd like to thank you for the time that you have been with us, the interest that you took in our research. And I wish you a very good fair.